Okay, so let's get started. Thanks everyone for coming to this week's C3 AI DTI seminar series. My slides is frozen. Okay, yeah. So the C3 AI DTI mission is to attract the world's leading scientists in a coordinated and innovative effort to advance the digital transformation of businesses, government, and society. And especially, it is by and large very supportive for research work that brings interdisciplinary study, including machine learning, computer science, economics, and engineering, to solve the breakthrough of science and engineering topics that is of great societal values. So I want to take a moment to pause here to acknowledge the academic as well as industry partners of the Institute. So this semester, we have a very exciting series of talks. And these talks have a common theme that focus on incentive design and learning for societal systems. These are the list of upcoming speakers for the rest of the semester. You can find their the information of the speakers as well as their abstracts on our website. Also, you can find the slides as well as recordings of the past speakers of this series, either on our website or on our YouTube channel. And if you don't want to miss our events in the future, please subscribe to our newsletter. Okay, so today we are very excited to have Professor Tamer Basar to talk about his research on inducement of desired behavior via soft policies. And Professor Tamer Basar is with the University of Illinois, Urbana-Champaign, and he's currently a Swanland Endowed Chair Emeritus, as well as Professor Emeritus of ECE and Research Professor at CSL and ITI. He has served at UIUC as Director for the Center of Advanced Studies, Interim Dean of Engineering, and Interim Director of Beckman Institute. His research has broadly included stochastic teams, games and networks, robust control, multi-agent systems and learning, data-driven distributed optimization, the spread of disinformation and epidemics, security and trust, energy systems, and cyber-physical systems. He is a member of the National Academy of Engineering, fellow of several societies, and recipients of many major awards, and most recently one is the Wilbur Cross Medal from Yale. He also holds honorary titles from various institutes in both Europe and Asia. Okay, so without further ado, let's give the floor to Professor Basar. So in this 1 hour seminar, we will have 15 minutes of the presentations, while the rest of the 10 minutes will be left for Q&A. Please use the Q&A feature to submit your questions, and we will ask your questions for you at the end of the talk. Okay, so thank you, Tamer. The floor is yours. I will stop sharing and you can share your slides now.
Thank you. Okay, so can you see it well?
Yes, yes.
Okay, well, it's a pleasure to be invited to give one of these talks in this series. And the spring series, as you have heard, is on the theme of incentive designs and learning for societal systems. And I picked a topic which I think goes well with that general theme. It's partly an overview of past work and partly some new ongoing work, which I'm going to discuss, but it will be in a broader framework, and there will be some technical details also. That's why I have as the subtitle mathematical theory of inducement. And also you may wonder why I have in the title via soft policies. And I'm not going to talk about threat policies, like an agent telling another one, you have to act this way. If you don't act this way, then you'll have heavy penalty. So that is not, it will be out of the scope of this, and that's actually not that interesting mathematically. So, so the outline of the talk is as follows. I'll talk about inducement, incentivization, persuasion, and so on. These are at a higher level. They all relate to a similar type of behavior on the parts of agents. I'll particularly talk about two different types of inducement. One is, which I'll call type 1, as shaping preferences or utilities. And the second one is on shaping perceptions or beliefs. And first, I'll talk about the shaping of preferences. And these are all, both of these actually lead to games. And definitely you need multiple agents to be able to talk about inducement or incentivization. And in the case of shaping of preferences, there is an underlying game, and I'll talk about the simplest one actually, but which captures most of the challenging aspects of problems of that type. And any direct approach towards solving these problems as a game meets formidable difficulties. And we have developed over the years indirect approaches towards solving the underlying mathematical problem, and this is related to mechanism design as well. And this brings in flexibility in shaping the preferences of individuals, as well as some elements of robustness into the design problem. And the second type is shaping perceptions, and that's again leads to a game, and it's both of them are actually Stackelberg games. That is, you have a hierarchy in decision making. Otherwise, you cannot talk about incentivization or inducement. And this it requires different mathematical approaches or tools to obtain optimal policies in that case. And this is related to deception, Bayesian persuasion, and SIT, which is strategic information transmission. And then I'll conclude. So the first thing I guess we have to clarify is I used several terms, and I said these are all sort of interchangeable. And these definitions are not my definitions, but they are from the dictionary, Webster. And so people, when you have the interaction between at least two people, you can talk about persuasion, one individual trying to persuade the other one. And that's the act of causing the other person to do or believe in something. We use the word inducement, which is essentially the relating to the same type of behavior, or incentivization. And I have put down here the dictionary in one sentence, the dictionary meanings. And then to some extent, we can talk about enticement, and you're enticing someone to do something, to act in a certain way. So how can we model such interactions? We definitely have a decision-making problem, and we need at least two actors to be able to talk about inducement. And one of these actors, or I can call them agents or players, tries to influence the decision-making process of the other agent. And there could, of course, this is as I said, you need at least 2 actors, but you can have more than 2 actors, and you could have possibly multiple actors on the receiving end and multiple influencers on the sending end, or you can have a mix of the two, or you can even have hierarchies in between, multiple layers, and where the agent at the top of the layer tries to persuade or influence the agent at the, say, the intermediate layer, and then that agent tries to influence the one at the bottom. And we have 2 types of inducements, which I had on the previous slide, which I call type 1 and type 2. In the first type, there is a direct input by the influencer into the utility of the other party. So essentially, what that results in is in shaping the objective function of those who are at the receiving end. And this is definitely, for example, as examples I could give government taxation policies or a pricing of electricity where the consumers would be on the receiving end, or pricing of internet usage, the bandwidth, based on bandwidth. So again, that would be on the receiving end. The decisions made by those who decide on the pricing policies would affect the utilities of those at the receiving end. And the second type is controlling the information flow. And so again, an agent at the sending side has some information which is relevant to an agent on the receiving side, but he could massage that information. And so therefore, massaging the information or distorting it would lead to some shaping of the belief formation at the receiving end. So these are both inducements, but they require different mathematical tools, as I will explain here in the rest of the talk, and different types of formulations, actually. And what would also be interesting is to have a mix of the two, and not much research has been done on that aspect. But both of them at a higher level lead to dynamic Stackelberg games. In other words, there is a hierarchy in the decision-making process. And in every Stackelberg game, if you have 2 agents, then you would call the first agent, who is the influencer in this case, as the leader. And so I'm going to use the L to stand for leader, and the other party would be the follower, which I'll use F. So let me now introduce this first type of inducement that's shaping F's, the follower's utility. So you have an agent, and this would be the sender or the inducer, and the one on the receiving end would be the inducee. So the inducer has the ability to impose her policy on F, on the follower, and based on the announced policy, which affects the utility function of the follower optimizes his objective function under that policy. And clearly the policy of the leader will be a function of the action of the follower. And so the question here that comes up, and that leads to a mathematical formulation, is how can one shape, or the leader can shape, the follower's objective function to align it with her, that is L's overall objective, to achieve an outcome which is more favorable to L. And in this case, you have full anticipation of, the assumption is full anticipation of the follower's response. And the sequence of moves in this type 1 is that there are essentially 3 steps, and the leader announces a policy which depends on the action of the follower. it could depend also on some common information that they both have, and which is shared by both of them, and also could depend on some private information that the sender has. And so therefore the gamma sub L, which is the policy of the leader, is a function of ZY as well as of UF. So this is announced, and then the F optimizes its objective function in view of this announcement. And that, let's say that for an announced gamma sub L, the optimization leads to some F sub F star, which is a function of Z, because this is the information that the common information that they both L. And then at the third step, the leader executes the action, and that action leads to a payoff for the follower as well as a payoff for the leader. So coming back to the sort of the electricity pricing, which I gave as one example of this type 1 type of inducement, is that the utility companies could announce a pricing policy. Based on that pricing policy, the followers, they optimize their use and based on how much they want to spend. And then the L comes back and collects whatever the based on the usage of the individual consumer, and then they both receive payoffs, which in this case are the revenues for the leader, and for the follower it's a cost that the payment that the individual makes. So the important thing here is that since the policy of the leader depends on the action of the follower, in this case, in the electricity example, is the usage of the follower, it gives L additional freedom to be able to shape F's preference, and therefore the objective function of the follower. And he can do it in a way that will benefit L, that will lead to maximizing getting the highest possible payoff within reason. And this could be done by possibly aligning F's objectives with the leaders. So the type 2 inducement is, as I indicated, is shaping beliefs. And this is based on the information flow that goes from the sender to the receiver. And so the leader, in this case, the sender, has access to some information of interest to the follower, and the follower seeks to learn this information of interest. And the question in this case is, how can the information interest be crafted by the leader so that the receiving agent will perceive it as desired by the sending agent? And this happening even when F is aware of the relationship between the received signal and the information of interest. So the leader can announce the policy as to how he's going to distort it, but not give full details of that. So this class of problems are also known as strategic information transmission, and it has connections to acts of deception and spread of disinformation, which is, of course, something that makes the headlines now. And it's also, of course, has connections to spread of epidemics as well. And so in the case of spread of epidemics with COVID, we have seen that there has been a lot of disinformation also being spread. So the two are quite connected. And again, in this case, you have to be able to talk about deception or spread of disinformation. You need at least two agents. And there's asymmetric information. The leader has access to an information of interest, but the follower does not have access to that. And there is misaligned objectives in this case. And the sequence of moves paralleling the one in type 1 is as follows. Now the leader, the sender, has access to realization of a random variable or a random vector, Z. For example, Z could be consists of two random vectors, X and Y, where X is the information of interest and Y is some private information, private to the leader. And based on Z, the leader generates a signal S using some policy. And this policy could be stochastic. And in constructing this policy, the leader anticipates, of course, F's optimal response. And F receives S or would receive a noise corrupted version of it, let's call it S prime, and will select a policy, gamma F, depending on S prime, that optimizes his objective function. And then at the third step, again, both L and F receive corresponding payoffs. And so depending on the choices of the objective functions of both sides, the framework captures problems of deception and transmission under privacy concerns, and it leads to quantification of persuasion capabilities of the sender. By how much can the sender persuade the follower? So there is definitely a parallel between these two types, and at the highest level, it's that they are both inducement policies. And in type 1 we have the ideal scenario. Note that in this case, the leader's policy enters into the utility function or the cost function of the follower. So the ideal scenario is to shape it in such a way that the follower actually ends up optimizing the leader's cost function. So therefore you can turn it into a team problem in a sense, even though it's a game problem with misaligned objectives. And so this corresponds to a mechanism design where, as I indicated here, the L makes F face an optimization problem totally aligned with her interest. In the second one, it's a parallel situation. The sender can impact the decision-making process at the receiving end by manipulating the information, not by manipulating the utility function. And so therefore this way can control the perception of the receiving agent toward her intentions, the leader's intentions. So let me go a little bit into the mathematical sort of derivations of the underlying policies in these cases, in these two cases. First, the type 1 type of inducement. Let's say that we have a state of nature is a random variable or a random vector X. The leader observes some Y, and the follower observes some Z, and both are correlated with X. And so therefore I have here three random variables or three random vectors. L also has access to Z. So this is important in this class of problems, to be able to induce a behavior on the part of the receiver so that the objective functions can be fully aligned. The leader has to have access to the information that the follower has. So which means that Z is a common random variable that's observed by both L and F. Now the action variables, the leader uses, as I said, Y and Z, and then uses a policy to generate an action. and the follower uses the random variable C and applies a policy on that and to generate an action U sub F. Now, in this case, we have the leader also has access to U sub F. That is the action of the follower, and the policy that the leader actually announces is not only a function of Y and Z, but also a function of U sub F. And I gave examples of the taxation policies and bandwidth pricing and internet pricing and so on. So the loss functions of both are, I call them as L sub L and L sub F, where the leader's cost function depends in general on the actions, on the two actions, as well as on the random variable X, and likewise the followers. And then you, because of stochasticity, you take expected expectations over these loss functions, given the policies of the leader, gamma sub L, which is of this form, and F sub F, which is of this form. Now, the Stackelberg equilibrium in this case, and that's what I'm going to talk about, and mechanism design problems are essentially Stackelberg games. So the leader, before announcing a policy, will anticipate the response of the followers, and so therefore will be able to compute this R sub F of gamma L. You announce a gamma sub L, and then there is a response. Let's assume that this is for each gamma L, there is a unique response. If it's not a unique response, the problem, one can look into robustifying this process. And then the leader will minimize, taking this, knows that this is going to be the response of the follower, and will minimize this overall policy as gamma sub L. And that leads to gamma L star, and that's the Stackelberg policy for the leader, or the incentive policy, we could call it. And the Stackelberg equilibrium is gamma L star together with the policy of the follower, which corresponds to this gamma L star. Now, the challenge in any direct approach to this problem is in this item 1 or bullet 1. Computing the note that the gamma sub L actually depends on the action of the follower, which the follower is going to optimize over. And so therefore, for different choices of gamma sub L, you will have different types of optimization problems. And at the outset, you don't even know whether gamma sub L is the best choice is would be a continuous function, for example. And you could have in the cost function of the follower could be, say, a quadratic function in terms of its action variable, as well as the action variable of the leader. But if the leader picks a nonlinear policy, then you lose the quadratic structure. So there is a big challenge in direct computation of RF gamma L, and so therefore in this minimization, in carrying out this minimization problem. And the main thing, as I said, is because the follower's cost function depends structurally on the choice of gamma sub L. Now, one important point here, which is of course an obvious observation, is that if both of them cooperate, if both the follower and the leader can cooperate in minimizing the leader's cost function, this provides a lower bound on this Stackelberg cost. And because the leader cannot achieve anything that's lower than this. And so therefore the indirect approach, which I'll have on the next slide, addresses this issue. To what extent can this infimum be achieved by a policy by the leader? And so instead of optimizing, instead of computing R sub F, you avoid, you get around this difficulty of trying to search all possible policies for the leader and see which one leads to the best cost. You simply find one which achieves this infimum, for example, if that's possible. And it turns out that for a large class of problems, either that is possible, or one can find another achievable lower bound, and then find the leader's policy which will achieve that. I'm not going to talk about this one which is not optimum, but there are several references that I can provide for that type of a computation. So this indirect derivation of the Stackelberg equilibrium is you find the optimum team performance for the leader with F fully cooperating. So this is you minimize JL. So this is the best the leader can expect, the minimum value of this over all possibles, given the information structure in the problem. But now there is redundancy of information. So this is in a sense, a static optimization problem. It does not depend on the actions, the follower. That's the difference between FL and gamma L. Gamma L depends on the action of the follower, but FL depends just on the random variables. And so, but there is this redundancy of information for L. L has access to the information that the follower also has access to. So that if you lift it up to the policy gamma sub L, there are there's a very rich set of solutions where gamma L would satisfy as the side conditions. So which means that we're looking at policies where if you replace U sub F by F sub F star or dagger Z, then you end up with FL plus, which is this. Okay. So we can therefore restrict ourselves to policies of that form, going from the most general class of policies to these special ones, and then see whether the lowest possible value for the leader's cost, which is this, can be attained when the follower actually responds to that policy by optimizing his own cost function. Now, one class of such policies is this additive one, where the first part is what we have here, FL dagger, and then the second part is a function of U, F, the follower's action variable, and F sub F, which is the optimal solution here, where G has the property that it vanishes at the origin. So it's 0 when this is equal to this. So therefore, you substitute this into the follower's cost function, and then see whether you can pick a G in such a way that the minimizing solution for the follower will have the property that it will be exactly this. If that's the case, then we have the Stackelberg solution. Okay, so that's we could call this as an incentive policy as well. So you could call this as a penalty if the G, if the F, if UF is not picked to be equal to this, and that would be in a sense a threat policy. The leader could say, if you don't pick UF to be equal to this, this is the penalty that you are going to have. But I'm interested in soft policies here. So the question is whether we can find a G such that it will have that property, that the follower's cost function will be aligned with the leader's objective. Okay, so this is the incentive problem. We want to find the gamma L star. such that, as I indicated, when you use this for the leader, then the followers minimization problem will lead to ft. And then when uf equals to this f sub f, then you end up with the leader's optimal solution. And this is quite a rich class of solutions. And if there is more than one, then this opens the door for additional specifications, such as robustness to inaccuracies in the knowledge of problem parameters. Okay. And one result, so of course there is, if one can come up with some linear incentive design, that's quite desirable. And in fact, there is under some fairly non-restrictive conditions, such as the Fresher differentiability, weak continuity of the Fresher derivatives, and strict convexity of LF in both UL and UF. And when we work in a Hilbert space of policies, then there does indeed exist such a policy where the G becomes a linear function, and there is a linear bounded operator in this case, mapping U sub f to the appropriate space, where this is the adjoint of QZ, that linear bounded operator which satisfies this. And one can actually show that there actually exists such a policy. Okay. And the main tool in this derivation is the Hambana theorem. You have, that's why you need the convexity, and you will have a supporting hyperplane to that convex function. And so clearly, in fact, from the Hambana, this is a linear policy, but there could be also nonlinear policies. And so therefore, if one wants to go and look at, so which ones are more robust to imprecision in the followers, for example, cost function that the leader may not have access to, then there is an additional optimization problem that one has to solve. But at this point, I'm assuming that the precise models are known, and so therefore this is the linear bounded policy is one that we can live with. Now the QZ is generally non-unique with a possible nonlinear dependence on Y and Z. For example, if we have a scalar linear quadratic Gaussian game, you have a quadratic cost function Gaussian random variables, then Stackelberg equilibrium policy for L is of this form. So LIN stands for linear. I wanted to fit this all on one line. So you have a linear YZ. So this is the FL, what I had. And this is the incentivization part. What the gain here is a nonlinear function of Z and linear in Y. So linear function of Y, Z multiplying another linear function of Z. So you have a quadratic term here in Z, and here you have another quadratic term in Z, and plus a constant. And multiplying this, again, note that if UF turns out to be equal to this function, which is the optimum, this linear Z is the team optimizing solution for the follower, then this term just drops out and you end up with the optimum solution for the leader. Now, one can actually extend this to multiple induces. And so you could have multiple followers. For example, one possibility would be the leader does not observe the actions of let's say that there are n agents on the receiving end, but the leader does not have access to each one individually, but has access to the sum of these. Then one can actually show that under, again, some conditions, there exists a Q function which induces each one of these. And this is, you need some symmetric conditions and so on for that to happen. Each one of these to the team optimal solution, to a solution which is most desirable by the leader. In that case, the most desirable policy would be from the part of the followers is the sum of these Fs, because that's what the leader would be looking for. And then there's a corresponding to leader's optimum policy. And one question that comes up now, I have a finite number of followers. What happens if I have a very large population of followers? Is it possible to incentivize a high population? Well, that's not possible. And at least with moderate effort, without going to high gain, because QZ grows with N. And we have some recent efforts in bringing in an intermediate sort of an agent in order to overcome this difficulty. So this essentially says that you cannot incentivize, you can incentivize a finite number of receivers by a single leader, but you cannot incentivize an infinite number of them. And you can have incentive problems with multiple decision hierarchies, and that's also tractable with Nash equilibrium at each level with multiple players. And at intermediate levels, the followers, you can have, when you have multiple levels, then let's say that you have 3 levels, the intermediate level agent will both be a partial an inducer as well as an inducee. Will be induced by the one at the top of the hierarchy, but will be able to induce those followers at the bottom of the hierarchy. So these are all interesting problems, and I cited here one early reference that deals with those. Okay, so let me talk about inducement, the second type of inducement now. Move on, shaping the followers' beliefs, and I had this slide earlier, and just to remind you what the problem was. In this case, the information flow is from the leader to the follower, but the information is manipulated by the leader in an attempt to make the follower perceive the actual environment or whatever the information is carrying in a way which is more aligned with the interests of the leader. Okay, and this is also a slide I had earlier. This is related to deception, spread of disinformation, and so on. So I want to sort of mention at this point that our Center for Advanced Study this academic year has every academic year we pick a different sort of a theme, and this one was on disinformation and combating fake news, which of course, as I indicated earlier, which has attracted top national and international attention, and particularly with also the recent war in Ukraine. And so this is from the center's website. It's essentially conspiracy, misinformation, and the infodemic. And you can go to the center's website and take a look. This is looking at it, this topic from different angles, not only the angle that I'm taking here, but from the legal perspective, political perspective, economic perspective, and so on, what disinformation leads to, the loss in all kinds of things. So coming back to the mathematical framework for this type of problems, we again have non-cooperative agents, L and F. They have different objectives because F wants to learn the information of interest, L wants F to perceive it as she desires. the information of interest in this case is drawn from a distribution, and the distribution and the objectives are common knowledge. Now, there is lack of cooperation, of course, naturally by the nature of the problem, and we have non-aligned objectives. This again leads to a non-zero sum dynamic game, but of a different type than the one that I discussed as corresponding to type 1. And again, it is asymmetric information. Any game with asymmetric information is very challenging to solve. And one has in this type of games, Nash Equilibrium with non-cooperative players, you have Nash Equilibrium, which gives the players symmetric roles, or Stackelberg Equilibrium, as I discussed earlier. My interest here, I'll be talking mostly on Stackelberg Equilibrium, but I also want to mention, to have one slide on Nash Equilibrium, because that's how this class of problems, the strategic information transmission, were introduced in the economics literature first. And definitely the Nash Equilibrium and Stackelberg Equilibrium, as we are going to see, will lead to structurally different equilibrium policies. And also they require different mathematical tools. So in the simplest possible one is this communication or information transmission problem, where here you have a sender, and there is an information of interest X. That's what the receiver is interested in knowing. But there is some private information as well to sender, or you can view it as a bias. The sender wants to introduce a bias into the transmission. So the G is a mapping which applies on X and theta that generates a signal which is sent either over a noisy channel or over a noise-free channel where W may not be there to the receiver, and the receiver wants to come up with an estimate of the information of interest, which is X. Even though the X was corrupted or manipulated by S by bringing in a bias theta. So here is the two types of cost functions, again consistent with what I just said. The receiver wants to come up with an estimate for X, receiving a manipulated version of X, manipulation depending on theta, whereas the sender wants the receiver to estimate a biased version of X, that is X plus theta. Okay. And so if we did not have any theta, this would be the standard information transmission problem of the Shannon type. So we have a non-zero sum game, and as I indicated, we have both Nash and Stackelberg equilibria, and Stackelberg is what I'm interested in here, but let me just mention in passing that the Nash equilibrium essentially ascribes symmetric roles to the players, and but still it's an asymmetric information structure because the Y depends on the policy of the sender. And the Stackelberg one is what I had introduced earlier. The leader will have to, the sender will have to see what the response of the follower is going to be, how R is going to respond to G, and take that into account and optimize his or her cost function. Okay. Now, this is as far as I will talk about the Nash equilibrium. This goes back to 1982. There is a very well-known paper by now, very well-known in which appeared in Econometrica by Crawford and Sobel, who looked at the version of this from the point of view of Nash equilibrium, where the X has bounded support, theta is known, and and there's no noise. So what they showed is that all Nash equilibria, and there are multiple Nash equilibria, are non-injective. So which means that what the sender does is comes up with some partitions of the message space, and the partitioning of the message space depends on theta itself, and then sends messages over each. So this is like quantization, and definitely quantization brings in errors, and the question is, how can you pick these cells, this partitioning, in such a way that the perception on the receiver end will be more aligned with the objectives of the sender. Okay. And we can also look at view this as an adversarial problem, where I think of the S as an adversary, and wants to sort of distort the message that's being sent. And in this case, the best policy or the worst for the system, for the adversary, is to quantize the source output in a specific way so as to deceive R. And in this case, the quantization occurs solely because of the mismatch between the two objective functions. And so this is called in the literature as cheap talk. There is also the noise talk version of that. Now, as I indicated, and I'm also running out of time, the Stackelberg equilibrium. So the solution for the under Stackelberg equilibrium is quite different. And for example, for the quadratic Gaussian case, it's essentially unique and linear, regardless of whether you have channel noise or not. And there's a comprehensive treatment of that problem and several other issues, privacy issues, and so on, discussed in this proceedings of the IEEE paper going back to 2017. So let me just share with you the structure of the solution. The best the Stackelberg leader can do is send a linear combination here. The X, theta, and W, when we have noise, are all Gaussian, and is to have a linear combination of X and theta, where the A, B, and so on are computed this way. Of course, when you have a linear transmission, then the best on the receiver end will be the conditional mean, which is going to be linear in Y. And so I'm going to skip this. When we have a noisy channel, the solution is again linear. In the case of noisy channel, you have to put a power constraint here. And so you scale up the solution that we had obtained earlier, scaling it up so that it will match this power constraint. And the best policy for the sender does not depend on the noise variance. So that's an interesting observation. And these are the expressions for the Stackelberg cost for the leader and so on. So the question, one question, interesting question, and this is, I'm looking at this bottom part, is how much does the receiver lose as compared with the what's called the Gaussian test channel if the objectives were totally aligned? Okay, so that's known as the Gaussian test channel or the standard Shannon problem, and definitely does worse in this case. So it is 1 plus a positive quantity, and this is what we can call the price of deception on the part of it. This is how much the receiver is hurt as a result of this. So there are several recent results, and I'll not have time to go into these, where the scalar solution is generalized, is extended to general quadratic loss functions, and general distributions for the random vectors, continuous as well as discrete. And these problems all lead to non-convex optimization problems on the sender side. And one has to introduce indirect methods, finding bounds for the cost, and then showing that these bounds are achieved. And the main reference is a paper which has just appeared this month in the Transactions on Automatic Control. So anyone who is interested in this, either I can send you the paper or we can discuss this further. And so I'm going to, I think I am running out of time, but I have here 2 slides before I get to conclusions. In this most general case, with again a quadratic cost functions, but the multi-dimensional problem, there is one possible formulation, or it captures a general sort of a framework, captures several special cases. One of them is the deceptive signaling game, where there's a private information Y, which you may view it as the bias, information of interest X. So the leader wants the follower to come up with an estimate of Y, whereas the follower is actually interested in an estimate of X, but the two are correlated. And another special case is what we call the persuasive privacy game. And this is one, there is the leader, X and Y are again correlated, but the leader does not want the follower to have access or to have drive information on this private random variable. So therefore, the leader's cost in this case will be like a zero-sum cost, where wants the receiver to come up with an estimate of X, but does not want the receiver to have a good, reliable estimate of Y. Whereas the receivers is quite the opposite, wants to have both an estimate for X as well as one for Y. Now, I'm going to skip this. There are sort of several tools that we have used in solving these problems using completely positive matrices, co-positive matrices, and the dualities, and SDP relaxation as well. But this is all in the paper. Now one can extend these from single sender receiver to groups of senders and receivers, and there are some interesting issues that come up there, and this is some of it is a current research topic, and I want to another one is the multi-stage strategic information transmission problem, and when you go to multiple steps, then there are issues as to how much information you want to disclose at each stage, and this is a very sort of a relevant quote from Abraham Lincoln, who says you can fool some of the people all the time. This is related to deception. All of the people some of the time, but you cannot fool all of the people all the time. And indeed, when you formulate deception problems for multi-stage scenarios, then you have something which is where this quote becomes very relevant. And some of these relevant references on this topic, the multi-stage topic, are given as follows. So let me conclude that I discussed 2 types of inducement mechanisms, and they require totally different and non-standard approaches. As future work, as I indicated at the very beginning, a mix of the 2 would lead to an interesting 3rd class of problems. And also, and this brings in, this is the only slide where I'll talk about learning. We are at this stage where we can incorporate machine learning techniques into derivations in model-free settings. So that's an interesting future sort of work. And regarding the type 1, any powerful incentive design mechanism will require redundancy of information. Because to be able to achieve full alignment or even partial alignment between the objectives of the follower and the objectives of the leader, and to be able to shape the objectives of the follower, you need some monitoring mechanism. And the only way you can monitor things from the point of view of the leader is if you have access to the information, at least partially, of what the follower has. And I mentioned briefly the robustness issues, and that in the high population regime, there are still very relevant research issues and challenging, and this is currently under study. And in the case of shaping of beliefs, again, it's an indirect approach that we have brought in. And one interesting class of problems would be to bring in elements of robustness to type 2 as well. And one way of bringing this would be through risk sensitivity, and which brings in an element of robustness into the solution process. So I'm going to stop here, and I did go over time, but I hope it was okay. Thank you.
Thanks, Professor. We are going to open for the questions. So first, is there any question from the panelists?
I have one question. So I guess in Stackelberg games, you need to know the utility or the cost for the follower, right?
Yes.
So
yes.
What is known about situations where you don't know that and you have to learn it?
Well, one, there are two. I mentioned, Srikant, this robustness issue. So if you have multiple solutions to the problem, and definitely most of them have multiple solutions, then you can pick one. You can parameterize the follower's utility function, and then you can have a nominal value for that parameter, and then you design one which is least sensitive to variations around that parameter. But this, of course, assumes that you have the nominal value. Now, as far as if you don't know about it at all, and you can still parameterize it as in reinforcement learning, and that's still a very active area of research. And of course, in that case, you need iterations. It's more like a multi-stage Stackelberg problem rather than a single stage one, because you have to have past information on the behaviors of the followers or of the receivers to past policies, so you can so that you are able to tell something about what their utility functions are. So that's indeed a very current area of research, which brings together incentive designs and learning, and some of the and it's not a standard reinforcement learning problem, because there are all these other elements there, the hierarchical structure and so on, which is I'm pretty sure the years to come we will have progress made in that on that class of problems.
Thank you. So there is questions from the audience about the applications of these results. So from Johnson Street.
Yeah, the application is definitely, I mean, the first type is the first type of inducement I had, which is mechanism design, and we have seen many applications of mechanism design in economics, and as well as in engineering. I mean, I gave examples of, for example, the utility companies deciding on pricing policies for different times of the day, what should be the pricing schedules. And they do that by taking into account possible behavioral patterns of the individual consumers. And likewise, the internet users would be affected by the pricing policies depending on the bandwidth, amount of bandwidth they use, and so on. So that's one. For the second type, it is disinformation, is the spread of disinformation is definitely, you want to try to stop misperceptions on the side of the formation of misperceptions on the population, and the question is whether you can view the sender in these cases as either hostile parties who deliberately want to do that, and then whether you can intervene and change that, the message that is being transmitted, or have multiple senders. And because this is not something I have discussed but you can also have multiple senders who are distorting the messages in different ways. And so therefore on the receiving end, the receivers will have to pick one or the other, whichever one they can trust more. So the trust building is part of that as well. But this is the main foundational work where before you even start talking about trust, to find out the extent of the manipulation that one can do in changing the perceptions on receiving it.
Thank you. So I do have one follow-up related to application. So I think you mentioned two types of information design, like the Crawford type, which doesn't require that the sender to commit to their strategy. So the sender can change their strategy, can be strategic, and when there is signal is being interpreted by the receiver, they're going to infer back what is the equilibrium of the sender. While in the later part where you present the more recent work on information design, so that part will require the sender to have commitment to their strategy before they even receive the signal. So I was wondering, like in engineering systems application, what do you think, like which one will be more suitable to use in what scenario?
I think even in the first one, the sender, if there is for example, I'll give the taxation policy. The government will announce a taxation policy and for 2021. And when 2022 comes and you have to have your returns sent, they cannot change it. So there is this issue of credibility. And so I'm assuming all along that that there is some, not some, but the sender is credible in that sense. In other words, if a policy is announced, then the sender will stick to that policy. But in deciding on that policy, you have to take into account possible responses of the followers in that case. Now, in a credibility, of course, to be able to develop some trust on credibility, you need a multi-stage problem, because you have to know how the sender has acted in the past, and if it's not credible, then this framework does not work at all. So there is a trust, formation of trust, which goes along with these. So in a sense, both of them, as Stackelberg Equilibria, built on credibility and assuming that the sender will not have any incentive to deviate from it. Now, you can come up with formulations where even if the sender has an incentive to deviate, it would not, because it's going to hurt them. And these are stronger, more robust solutions. I haven't talked about these, and definitely there is that additional sort of element in all these.
Yeah, thank you. That makes sense.
Sure.
Yeah, thank you. So we are a bit over, already a bit over time, and thanks everyone for coming to the seminar, and thank you to our speaker, Professor Basar, for the wonderful talk. Yeah, thank you.
Thank you.
Thanks all.